but now it can involve 3D shapes. So you'll need to know how to use or recall the properties of two-dimensional shapes. Probably more importantly than three-dimensional shapes, because the properties that you'll use in a three-dimensional problem are probably Pythagoras theorem, trigonometry, and two-dimensional shapes. So you'll be looking at faces and sides and stuff. So you need to know triangles, different types of triangles, and the properties of some triangles, particularly equilateral, right-angled, and isosceles. You'll need to know about squares, rectangles, rhombi, trapeziums, parallelograms, and also regular polygons. So I'm not going to go into those in too much detail now. I'm kind of going to assume. But the things you need to know, stuff like all of these things here are actually trapezium. Trapezium is a really large grouping. It's just any quadrilateral where it has one pair of parallel sides. So a square has two pairs of parallel sides, therefore it's a special type of trapezium. But when you get a question that quotes something like a rectangle has vertices A, B, C, D, you need to know straight away, okay, we're talking about a shape that has opposite pairs that are parallel, has right angles, which then brings into play things like the dot product, and that type of stuff. A rectangle has diagonals that are equal length and bisect each other, and the opposite angles on the diagonal are equal, those types of properties. So I would suggest that as you're working through this, you start building up a list. That's kind of assumed knowledge. At this stage, if somebody is making a what do I need to know before I do specialist maths video, that might be on it. Any questions on that? Does anybody want to tell me anything they know about regular polygons? What's a polygon?
A shape that has three or more sides.
Yeah, so an n-sided shape, whatever. So a polygon is just any shape. A regular polygon is a polygon that has all equal sides. So when you are looking at shapes and you see what most people think of as a hexagon, which looks like this, so people are like, oh yeah, that's a hexagon. That's a regular hexagon. All the sides are equal and it will always look like this. Here's another hexagon. That didn't quite meet. There's another hexagon. Now most people would look at that and not think, oh, that's a hexagon. But when you count up the sides, it just doesn't look like what we would consider to be a hexagon. So if you're thinking of a hexagon, you're probably thinking of a regular hexagon. And a regular hexagon, like all of them, all the sides are equal, all the internal angles are equal, and all the internal angles are equal to n times 180 minus 360 divided by n. So there's a pattern to the size of the angles, although that's not so important. Usually it's just knowing that the sides are equal that's really important there. Also, if it brings about right angles, etc., could be important as well. Here's a couple of things you need to recall. We talked about these just the other day. And, oh, there we go, we're off, it's working. So, if vector A is parallel to vector B, and they share a point, then A and B are on the same line, they're collinear. You get that collinearity from that. We talked about that last lesson. If vector A is perpendicular to vector B, then A dot B equals 0. And in reverse, if A dot B equals 0, then A and B are perpendicular. And also, this is one we haven't talked about for a little while. The linear combination stuff, which we did talk about briefly. The linear combination of A and B is some constant times A plus some constant times B. Now, if you get this relationship, and it comes up in a couple of the questions, where MA plus NB equals PA plus QB or whatever, then necessarily it has to be true that M and P are equal and N and Q are equal. That has to be true. And there's nothing, that's the only way to get that to match up. So that might come up as well. Otherwise, the rest of it's all just those basic principles that we talked about in that initial vector review. A can't be parallel to B, by the way, in that case. I'm just going to run through and do a couple of examples with you, but there's 24 questions in an exercise for a reason, because every example is going to be slightly different. So if you get a question like this, it's either going to be really easy or it's going to be a complex for me, a complex one for you. It'll be one of the harder questions in the paper. Most of them are. So you'll find this exercise may be more challenging than most of the stuff you do in this topic, this term, but that's where we are. So example 2. Prove that the midpoint of the hypotenuse of a right-angled triangle is equidistant from each vertex. So if you get a question like this, there's a lot of words in there that you've got to break down. You're thinking prove, it's a prove question. Got a hypotenuse, it's a right-angled triangle, and so that has a hypotenuse. We're talking about the midpoint of the hypotenuse. I've got to break down what equidistant means and think about the vertex. There's a lot of mathematical language in there. Your best bet is almost always going to be start with a diagram to recognise what you have, what you know, and what you can use. So here's my diagram, and it's a right-angled triangle, and I've missed it. There, let's try that again. Okay, there we go. Right-angled triangle, that's a right angle, which is not as important on a diagram, but it's going to lead me to a dot product kind of situation. And I'm going to call this A, B, C. And then I need a point that's my midpoint. So I'll do that in a different colour. That's here. We'll call this D. And I need to prove that D is equidistant from A, C, and B. Now, I already know that D is equidistant from B and C because it's the midpoint. So by definition, it has to be the same distance from both, yeah? So it's really just proving that this is the same length as that. That's what I'm trying to prove. Or that this is the same length as that. Once I've done that, I'm pretty comfortable. And again, that comes back to that property idea. So you needed to know about triangles, right-angle triangles, what a hypotenuse is. It's all basic stuff, but you're going to have to recall it as we move forward. So I'm going to start by defining some names. And when we're doing this definition, like I'm going to remove my need to do A, B, and AC, etc. I'm going to try and define the least number of names possible. So, for example, I could call this A, and this B, and this C. But if I do that, I'm going to create a situation where I've got three things when I actually only need two. Because if I've got A and B here, I can define that from A and B. So I'm going to do that. So I'm going to start with, let's let A equal AB, and let's let B, it's going to seem counterintuitive the way I'm doing it, but it'll work, equal AC. In fact, I might even do it as that side definition. So I'll call that C. I've got C and B. So side C is opposite angle C, side B is opposite. That seems to be something that we typically do. And I also know, therefore, that CB is equal to, so to get from C to B, I've got to go along CA and then along AB. So that will be negative B plus C. So we happy with that? So I've got that, that value there. So if CB is negative C plus, sorry, negative B plus C, what's CD? Half of that. So that's pretty easy. So I can do another therefore statement. CD, that looks like complex numbers, is equal to a half. And I'm going to change it around, C minus B. So there's my next statement. So I've got my CD now. That's pretty good. And I can work out the length of CD. I can't actually work it out, I don't know the numbers, but I can work out an algebraic representation for the length of CD. What I need now is my AD. So what is the value of AD in this case? So I can write down AD is equal to, which way do you want to go? Let's do it. A to B plus B to D. Does it matter? Okay, yeah. So it doesn't really matter. It's going to work out the same way, but it's going to create that to there. We just have to recognise we have to flip it over. So I might do it the other way just to avoid any confusion if you're looking back through later. But right now in this space, it doesn't really matter. And we've also worked out CD already, so we may as well use CD. We've already worked out. So AC is equal to B plus a half C minus B. And if I expand that out, I get B plus a half C minus a half B. And then if I simplify that, I get a half B plus a half C. Happy? Okay. Can I now prove that that is the same length as that? What do I need to determine now? This is kind of my setup. I need to do the magnitude. So this is RTP, by the way. You should have seen it before with me last year. RTP, required to prove. I really want to prove that the magnitude of CD is equal to the magnitude of AB. Now we're talking about magnitudes, so it doesn't matter if I say CD or DC or AD or DA, the magnitude will be the same because it's a length. Oh, I said AD, didn't I? I just wrote something different. So CD is equal to AD, that's what I want to prove. I know my CD, so that's equal to a half C minus B, the magnitude of that. And I know my AD, which is equal to a half B plus C. Now, is this going to work out? So how do I determine the magnitude of those two? How does the magnitude break out? That's what I'm required to prove. Let's look at an individual one. Does anybody know another formula that involves the magnitude? Sorry? Say it again. Dot product. So what dot product formula involves the magnitude? AB cos theta has magnitude components in it, yep. I just want to see what's, I've got to remind myself what's on here. So the magnitude is, got to remind myself the formula. Yeah, no, let's remove that. So let's talk about the dot product between two things. So we have the dot product here of AC and AB equals 0, yeah? I can't remember the expansion off the top of my head. Okay, we're back, and I did not have to go off and spend 10 minutes trying to work out how to do that. Our next step is going to come from, this is what we're trying to prove, B dot B, or actually let's do it generally. Q dot Q is equal to the magnitude of Q squared. So we're going to use that, except we're going to use it in this case for this problem here. Our required to prove is that CD, the magnitude of CD equals the magnitude of AD. So we could square both sides of that, and then we're going to expand that. So what I'm going to do is start by taking the left-hand side of our required to prove, which is the magnitude of CD squared, and I'm going to square it. And I will have a look at what both sides look like after we've squared them both. So this becomes the magnitude of CD squared, which equals the magnitude of a half, what was CD again? C minus B squared, and that's equal to a half C minus B dot a half C minus B. So this, without a what, sorry?
A1 and A2. That's no.
Without A1?
Yeah. A dot B equals A1 B1.
Oh, yeah, that's what we're going to do now, the expansion. Now, this is a scalar component. Half and a half can be taken out. So I'm out with a quarter at the front. And I get a quarter here. And then my dot product can be distributed as we'd expect. So we get C dot C minus 2 C dot B. Is it minus? Yeah, it is minus. Plus B dot B. And the trick here is to recognise that C dot B equals what? 0. Excellent. So remember, they are two perpendicular vectors. So if I write down here, that's perpendicular. So c dot b equals 0, and therefore that's equal to 1/4 c dot c plus b dot b, which I could write down as 1/4 of the magnitude of c squared plus the magnitude of b squared. But I don't really have to go this far because the other side's going to work out just as well. So that's my left-hand side. My right-hand side, give me a second, which I probably won't expand working-wise quite so in depth. My right-hand side is equal to AD, and I want to square that side to match it with the other one, with my left-hand side. So I could technically write that this is left-hand side squared, and then write down this is right-hand side squared. The other thing I could do is just do all this work I'm doing at the moment under a square root sign, and that would be a good way. So you're looking for good communication. There are two options for you. AD becomes a half. Now AD was half B plus half C. So half B plus C dot a half B plus C. The halves come out the front to make a quarter, and the B plus C becomes B dot B plus 2B dot C plus C dot C, and obviously the B dot C is equal to 0 again, and this becomes, that wasn't meant to move, a quarter of the magnitude of B squared plus the magnitude of C squared, and this is equal to the left-hand side squared, and therefore left-hand side is equal to right-hand side as required. So that was a bit of a tough one. A lot of these come back to that dot product and the dot product expansions. And the hint here is that it involves a dot product because there's a right angle implied in the question somewhere. So if you see that, you're probably going to assume 95% of the time there's a dot product thing involved. I haven't done many of these, and I know that I just found that tricky, that's finding that missing step. And I imagine that might be tricky for you as well, but if you do 10 of these, you'll find that it's working better. And this, I'm going to go out on a limb and say it's probably going to pop up once on your exam, your external exam. May pop up in your internal exam, but your external exams, those two double papers, which will cover most things. So there's a good chance it will pop up somewhere. Not this question, but something that's a geometric proof or reasoning type question. So get to know your expansions of dot products. We can stop there. We've proven that AD is equal to CD. We don't have to prove DB anymore, but you probably should finish with a statement, which I'll do in a second, to say, due to the midpoint, DB is equal to CD is equal to AD as required. So some sort of concluding statement to show all three of them are equal. I think that's it. Any questions? Just going to and say BD equals the magnitude of CD. Therefore, I'll do example 3, but I won't do it just yet.